All right, so now we've got our time-dependent Schrodinger equation. This complicated equation that we know it is an expression of the conservation of energy. And we know a little bit about psi, our wave function, and what it means. How do we solve this? Now we need to begin to solve the Schrodinger's equation. Well, the first step we'll take is we'll use the separation of variables technique. To separate, we're going to, just give you a heads up, we're going to separate the position variables from the time variable. So let's, separation of variables technique. It's always our first line of defense in solving partial differential equations. We're going to assume that our function can be represented as the product of functions of single variables. In this case, we're going to say we've got a lowercase psi, which is a function only of position, and times phi, which is a function of time. So we're going to assume that capital psi of r and t is equal to little psi of r times little phi of t. Now, this means that if this is true, if we can do this, then del squared of capital psi is going to be del squared of little psi phi. But phi is our Laplacian operates only on spatial variables, so we can bring phi out here. So this is going to be phi of t times del squared little psi of r. And the partial of capital psi with respect to t, similarly, is going to be our little phi, our little psi, that little psi we can bring through the partial derivative operating on phi, but our partial derivative is now, we can express it as a total derivative because phi is a function only of t. So we can even say that this is little psi of r times d dt, d phi dt. All right, so with that, our time-dependent Schrodinger equation, when we plug in our assumed form of psi, we plug this in, we'll have over here, we can pull out a phi, and here we can pull out a psi, and with a little bit of manipulation, we get phi of t times negative h bar squared over 2m del squared psi plus v bar psi and this is equal to I h bar psi of r d phi dt. Now, we can divide both sides of this equation by phi times psi. So we're going to divide through by both sides by psi and phi. And what we get on the left is 1 over psi of r times negative h bar squared over 2m del squared psi. We have simply v of r because our psi's cancel. And over on the right we have I h bar over phi, or phi of t, d phi dt. Now, we can observe that on the left, this is a function only of position. Position variables. And over on the right, this is a function only of time, or only of t. And this has to be true for all position and all time. And as we argued last semester in electromagnetics, applying the separation of variables technique, this is going to mean that this expression has to be a function equal to a constant, is equal to the same constant, and we're going to let that constant, that separation constant, in terms of the separation of variables technique, that separation constant is going to be, we're going to let that be equal to E. We're going to look ahead and recognize that's going to be equal to E. So this gives us two equations, one in position and one in time. And if we take our position, our function, our expression in time, this gives us, we set equal to E, and we multiply through a little bit, do a little bit of algebra, we find this differential equation, d phi dt equals negative I E over h bar phi. All right, that's from our right-hand side setting equal to E and doing a little bit of algebra to get this. Now, this gives us the solution to this. If we just set our amplitude equal to 1, then phi of t, that function, is equal to e to the negative I E over h bar t. And if we set our left-hand side equal to E, and then multiply times phi, our psi of r, we're going to come up with, and then rearranging a little bit, we come up with our time-independent Schrodinger equation, negative h bar squared over 2m, del squared psi of r, plus v of r minus e psi of r equals 0. So this, again, is our time-independent Schrodinger equation. What we will see is that our time equation here, our formula, is going to actually give rise to Planck's relationship, amazingly enough. And the rest of the hard work comes in solving the time-independent Schrodinger equation.